So far in phase equilibria, we've discussed three models for activity coefficient models. Those have been the one-parameter Margulies model, the two-parameter Margulies model, and the Wilson model. So hopefully these three models and these three equations are a good summary of what we've covered so far. I also wanted to quickly address, before I move on, a couple of other ones that your Sandler text mentions. So a fourth is the NRTL model, the non-random two-liquid model. And that is mentioned in equation 9.5-14a. These equations are getting very long, as you can see, to write out. So you can just reference these when you need to use them. And also I wanted to mention Flory-Huggins. So I mentioned at the very beginning how many models there are like this, and you just for illustrative purposes, how many there are. This is in equation 9.5-18 in Sandler. So a logical question that you might ask is, well, how do I know which model to use? And that is a very, very good question. Unfortunately, I cannot give you a good answer. There is not really situations when you would want to use one over the other, unless you have a situation where you're varying temperature, in which case the Wilson model might be good to use. Also wanted to mention, remember in the Wilson model that these lambdas are functions of T. So remember, the temperature dependence for the Wilson model is built in, and this lambda is a function of some other parameters that are not temperature independent. So a lot of these modeling approaches have different levels to them. Some models work better for some systems than others, and if you have a new system, really the best thing to do is maybe try out a couple of different models, see if they give you similar results or different results, and then try to do some experiments to see which one is modeling the behavior the best. And that gets me to another point that I wanted to make about all these models so far. So I didn't write out the non-random two-liquid and the Flory-Huggins model explicitly, but a common thread in these five models so far is that these all require some form of experimentation in order to fit some parameters. So if I circle where the parameters are, I'll highlight them with my blue highlighter. The parameter A is in the one-parameter Margulies model. A21 is in the two-parameter Margulies model, and A12. So these things I'm highlighting are all things that you would need to fit with some type of experiment. The lambdas, not the X2. So highlighted is parameters that must be fit by experiment. So the next logical question that you might ask is, well, do I have to do an experiment at all? Is there any other information that I can look to that would tell me what the value of these parameters are for the different components? And that leads into a branch of activity coefficient modeling known as predictive activity coefficient modeling. And as I mentioned, this is kind of the holy grail of thermodynamics and phase equilibria, is obtaining these predictive activity coefficient models. And these would be really great, because if we had a predictive activity coefficient model that really worked, we wouldn't have to do experiment at all. We could design systems without having to have any experimental data. We would just crunch the numbers and do it completely with an experiment or a simulation first, and then build our process from there. Whoops. So once again, in a predictive model, I need no experimental data. All parameters that I need are going to be able to be calculated based on stuff that I can look up about the pure components. So an example of such a predictive model, unfortunately, it doesn't work very well. And really, none of the predictive models work well enough that, to my knowledge at least, no processes in industry are designed with any of these predictive models. But again, I introduced them here because the potential is there to maybe someday somebody might produce a predictive model that could be used. And again, that would be the best case scenario for all of phase equilibria, is to use one of these predictive models to model everything. One of this is called the Van Laar model. So the Van Laar model starts with excess molar Gibbs energy divided by RT, as all the other ones do. The parameters for the Van Laar model are L21 and L12. So all these models have slightly different names for what they call their parameters, but the idea is the same. They're all just numbers that are making the data fit. L12, L21 divided by L12 x1 plus L21 x2. And I want to mention that the Sandler textbook uses different terminology here for the Wilson model. I'm sorry, for the Van Laar model, I think they use alpha and beta, and I've chosen not to use alpha and beta because I've used alpha and beta before. And also A and B are also going to come into play here, and I don't want to get confused with alphas and A's and betas and B's. So in the Van Laar model, you can apply the same partial derivative technique that I've gone through for the one parameter Margulies model. Once again, that would be a little bit too much steps and too much derivation to show. So I'm just going to go ahead and give you what the ln for the activity coefficients end up being. Ln of gamma 1 is L12 divided by 1 plus L12 x1. I hate how it's L12 and L21 as well because I get confused all the time. So it's not just you if you find these hard to keep track of. And this whole denominator is squared. And ln of gamma 2 is most of the time also in these activity coefficients, you can figure out what they are just by flipping it. So instead of L21 here, instead of L12 there, it's L21 in the top. And then 1 plus L21 x2 divided by L12 x1. And that's all squared. Now, where the magic in the Van Laar model becoming predictive comes in is that instead of using experiments to obtain the values for these parameters, L12 and L21, these can be described by the van der Waals parameters. And both textbooks actually have some interesting historical knowledge that Van Laar was a PhD student of van der Waals. So I like to envision just Van Laar and van der Waals in a lab meeting one day hashing this all out. So in the Van Laar model, L12 is equal to B1 over RT. And B is of component 1, by the way. So there's component 1, component 2, times the quantity square root of A1 divided by B1 minus square root A2 divided by B2 all squared. And L21 is the other one. So B2 over RT square root of A2 over B2 minus square root A2 over B2 square. Now, you may be wondering what A and B are, and these are terms that we've seen before. So this is where A1 and B1, A1, B1, A2, B2 are the same parameters as given in the van der Waals equation of state. Same parameters as the van der Waals equation of state. When I discussed equations of state so long ago, I mentioned that the van der Waals equation of state was one of the first equations of state to be cubic, and it wasn't really accurate. So again, with the Van Laar model, this is not the most accurate model that you can use, but it's really interesting from the perspective of you don't have to do any experiments once again. So I can't remember if I went over this. This should have been a topic that was introduced in your Thermo 1 class, but you can obtain the values for the parameters A and B by using the critical temperature and the critical pressure. So the parameter A for any component is 27 R squared TC squared. So this is the critical temperature divided by 64 PC. So TC is critical temperature, PC is critical pressure, and B is RTC divided by 8 PC. So TC is critical temperature, and PC is critical pressure, which are both things that can be looked up in a table somewhere. So again, it's a couple of steps, a few different hoops you have to jump through in order to use this, but ideally what you would do, so if you had a system that you wanted to model, let's use the water ethanol system again, you would look up the critical temperature, critical pressure for water and for ethanol. Those become, you plug these into these equations to get your A ethanol, A water, B ethanol, B water. Then you plug these A's into this equation to obtain your L's, and then you plug these L's into this equation to get your gammas, and then you plug these gammas into your Raoult's laws to finally find the dew point and bubble point pressure. So that's 3 levels of modeling that you have to do, but nowhere in there did I require any sort of experimental data. Now, the Van Laar model is, again, like I said, not very accurate. So some years after that, a couple of other researchers improved upon this. And instead of, well, let me see, I want to organize this a little bit better. One moment, I'm going to organize. All right, so here's how I'm going to say it. This is the Van Laar model for the activity coefficients. And then in obtaining what the values for L21 and L12 are, there's a couple of different ways you can go about it. The first is the Van Laar method, which I just described to you, in which L12 and L21 are ultimately functions of critical temperature and critical pressure by the van der Waals equation of state. There's actually a lot of theory that goes on in the back end here that would take me a while to get through. I don't truly care that you understand all of it. Just know that Van Laar method is based on the van der Waals equation of state. And once again, it doesn't really work well anyway, so there's not a whole lot of use in knowing exactly how it works. Another method that works a little bit better is an adaptation of this Van Laar model, which was proposed by Scatcherd and Hildebrand. Scatcherd, not Scratcherd. Scatcherd. Scatcherd Hildebrand model, or Hildebrand adaptation. So they're still using the Van Laar activity coefficient model, but instead of obtaining L12 and L21 based on the van der Waals equations of state, they do it slightly differently. So they say that L12, and I'm working off of the terminology in the Dom and Visco textbook now, but they actually describe it a little bit different. They use an M instead of an L. I'm not sure why they keep changing up parameters. Just in the interest of keeping things consistent, I'm going to keep it L12. So in the Scatcherd-Hildebrand adaptation, they say this is the molar volume of species 1 divided by RT times delta 1. So as soon as you see a delta, you know that there's going to be some other modeling going on. So delta 1 and delta 2 are going to be functions of something else. And L21 is equal to molar volume of component 2 divided by RT. Delta 1 minus delta 2 squared. And here, delta 1 and delta 2 are called the solubility parameters. And delta 1 is equal to the change in molar internal energy upon vaporization divided by molar volume of component 1. And delta 2 is the same, but for component 2. So molar internal energy of vaporization of component 2 divided by V2. Solubility parameters. And then once again, I know I'm repeating myself, but I want to make it explicitly clear that this is not all pulled out of thin air. There's a lot of work that goes on that is able to prove why L12 and L21 should be functions of the internal energy and the molar volume at all. I'm just showing you that there's a variety of approaches here, and this would be one example of how you would go about obtaining a predictive model. One more predictive approach, which is slightly more common, is called the UNIFAC. I like this one because of the name, but also because it's neat in how it works. And UNIFAC is an acronym standing for Universal functional activity coefficient model. Functional activity coefficient model. And what UNIFAC does is it takes into account which functional groups. So in organic chemistry, if you have like isopropanol, for example, right, this has a functional group of an alcohol. So the UNIFAC doesn't take into account that it's a molecule, or like what isopropanol is as a molecule. It just takes into account the fact that it has a alcohol as a functional group. And then it correlates that. So if you mix an alcohol with a, I don't know, a nitro group, for example, then UNIFAC is able to predict the interactions between this alcohol group and this nitro group, and then it calculates the activity coefficients based on that. Again, there's a lot more that goes on in the back end, but this is one of the options that you might see in process simulation software. So this is a common selection in process simulation software. Nobody actually works out UNIFAC by hand. I would venture to say that nobody really does any calculations by hand in industry for the most part. Common selection in process simulation software. So if you're interested in these, and I think I might prompt you in an upcoming assignment to look into these UNIFAC models a little bit more and write about what you've learned about. There's so much that goes on here. It's really mind-blowing to me that chemical engineers have been able to come up with all this stuff, and we still don't have something that works uniformly and universally every time. But hopefully this should give you a good introduction to some of the different models that are out there. In the other videos for today, I think I'm going to do some discussion about how the Gibbs-Duhem equation works into all this, and then also do some example problems in the third video. So that's all for the first video.